We had discussed regarding the conjugate beam method. So today we'll discuss how to analyze the slope and deflection using the principle of virtual work. So the principle of virtual work is that, so here you can just observe over here. So I have considered a structural system. I have considered a structural system, so which is subjected to set of forces, so P1, P2, P3, etc. So totally overall it is referred to as P force. I just repeated. So we have considered a structural system which is subjected to set of the forces P1, P2 and P3, wherein the total forces P1 to P3 is considered to be as the force as P force. So it is under the stable equilibrium condition, so which is as shown in the figure 1. Further, I'll consider a small element. So here you can just observe over here. One second. Yeah, you can just observe over here. So this is a small element which I have considered within this structural system. So within the structural system, and the stresses on the surface caused by the force caused by the P forces are shown in the figure 2. So this is the a small element, that is this is small element, so which is shown in the figure 2, wherein the stresses which is caused by the P forces are as shown by the arrow marks. Okay, so here I just consider let the body undergoes to set of the compatible virtual displacement. So I just consider that B1 is the body subjected to the figure 1 is the body which is subjected to system of forces, and figure 2 represents the stress in the small element which is represented as sigma P. Sigma P represents the stresses in the small element. So total stresses which is due to P1, P2 and P3 are represented as the stresses which is caused by the caused on the element, small element. So totally it can be referred to as sigma P, stress due to the P force. Okay, so next I just take, or I just assume delta D as the virtual displacement. So virtual displacement is nothing but it is the imaginary displacement or the imaginary deflection which is caused due to the forces. So let the body undergo the set of compatible virtual displacement delta D. So these displacement are imaginary. As I said, that virtual displacement is nothing but the imaginary displacement. So here this displacement is represented by the first figure in the dotted lines. So you can just observe the virtual displacement in the first sketch, which is represented by the dotted lines, and which is represented by the dotted lines. So while the body is displaced, the real force acting on the body move through these displacements. So whenever the real forces, that is P1, P2 and P3 are the real forces. So when it act on the body, it moves through these displacement. It is assumed that it will be moving through this displacement. Means, so initial position of the body is represented by this straight lines. So the final position or the deflected position of the body is represented by this dotted lines due to the action of the forces P1, P2 and P3, like that. So these forces and the virtual displacement, it must satisfy the principle of conservation of energy. So whenever these forces and the virtual displacements, it whenever it is assumed, it has to satisfy the principle of conservation of energy. So wherein the conservation of energy states that the the external work is equal to the internal work. So work done by the external forces, that is delta WE, the work done by the external forces is equal to the work done by the internal forces. So here it can also be represented as sigma Pi delta di is equal to sigma p I represents here the subscript of I represents as the forces 1 to 3, means p1 p2 p3, like that. So here sigma pi into delta d, force into the deflection, force into the deflection. So deflection is the delta d value. So whenever the real forces is acting, this is the amount of the virtual displacement. So whenever it is acting, the deflected position, if it deflects in the virtual deflected position like this, which is represented by the dotted lines, so it always it always follows the principle of conservation of energy as P, that is external force or external work done, or the work done by the external forces will be equal to the internal forces. So
Oh,
here the
ma'am, oh, sorry for disturbing, ma'am, but few students are waiting to join the class, ma'am.
okay. So one thing you just ask them, it is difficult to make it now, na? So I'll make it recorded. They can see that. Okay, let them know like that. Okay, so this is the pi into delta di. So this is the value of pi into delta di. So here pi represents the external force which is between 1 to 3. So delta di is the deflection. Delta di is the deflection. So which is from 1 to 3, means the individual deflection of the respective forces, the individual virtual displacement of the respective forces. Means suppose if P1 is there, so delta D will be delta D1. So P2 is there, delta D2, P3, delta D3, like that. So is equated to, it is equated to integration of sigma p, means this is the internal work done is due to the it is projected as for the elementary section. So sigma p into delta epsilon represents the strain. Delta epsilon represents the strain. Okay, so delta epsilon into dv. dv represents the individual amount of force, that is internal force on the elementary system. So this is the principle of the virtual work. So whereas if I just state it as a theorem, so it states that if the system in the equilibrium under a system of forces, if it undergoes a deformation, the work done by the external force is nothing but P. So is always equal to the work done by the internal stresses due to those forces. So whenever, if there is any equilibrium which has to be satisfied under a system of forces, so the forces undergo the deformation. So the work done by the external force, that is P is the external force, so which is always equal to work done by the internal stresses. So how much amount of load if we are going to apply, suppose for a body, if we are going to apply the load of 5 kilonewton, so if at all, if it is sustaining, means without any failure, if it is not if it is not deforming, means then the same amount of resistance will be offered by the body also towards the application of external load in the opposite direction. Correct. So therefore, it is always equal to the work done by the internal stresses due to the effect of those forces. Due to the effect of those forces means the external forces. So is it clear, all of you? Shall I proceed? Shall I proceed?
Yes, ma'am.
Yes, all of you.
Yes, ma'am.
So coming on to the next very important method, is called as unit load method. Unit load method. So here in this method, this is a principle in order to use the energy conservation method. So here I have considered a structure which is shown in the first sketch. So here I have considered a structure which is shown in the first sketch, and it is subjected to force P force, and it is also required to find the displacement at point C over here. So here you can just observe here. So I have again considered a structure wherein it is subjected to the system of forces, that is P force. So therefore I also considered a point C wherein at that point C I need to find out what is the amount of displacement which is caused due to the action of P force. So in the direction which is specified. So this is a direction which is specified. So first of all, I need to apply, in order to determine the deflection, I need to apply the virtual force at C, which is in the required direction. So here I'm going to apply the virtual force, means the imaginary force at point C. So after that, I need to apply the external load. I need to apply the external load acting on the structure as shown in the figure. So first of all, if I want to find out the deflection at a particular point for in some direction, so we need to assume some direction. So I need to find out what is the amount of deflection at that point by applying the virtual force. So here the virtual force is delta F first. So I have assumed the direction as it is going outwards. You can also assume it is going inwards also. So after the application of these of this virtual force, I need to next take the action of the real force which is as shown in the figure, that is P1, P2, P3. So with this for virtual force, it remains in the position, and the displacement of C here, it is required to be in the direction of delta. So here delta represents the imaginary displacement of the point C due to the load of delta F. So therefore, by using the principle of conservation of energy in the previous slide, what we have got, that is summation of internal work done is equal to the external work done. So by using that principle, so in the internal point which I have considered is C point, wherein the force assumed on that is delta F, and then the displacement to be considered here is delta. Due to that due to the action of virtual load, delta is the virtual displacement. So therefore delta F into small delta F into delta, where delta F is the virtual force and delta is the virtual displacement due to delta F. So it is equal to sigma delta F into delta L. So sigma delta F into delta L. So wherein here left hand side equation, it denotes the external work done by the virtual force delta F moving through the real displacement. So listen here. So delta F is the external load, which is an imaginary load, which is applied on the point C, wherein due to that action, I am getting the displacement of delta. That is the virtual displacement. So on other hand, the right hand side equation, this is the right hand side equation, so which represents internal work done by the virtual internal elements of the forces, that is dF. So wherein delta L represents the overall displacement. So suppose if I just take this is the internal element, so which is situated here. So this internal element will be having delta, I mean, L is the overall length. Okay. So if this element, if it is considered to be under the action of delta F, so therefore, yeah, the internal forces will be equal to sigma times of delta F, means algebraic sum of all these forces. So therefore, it is sigma delta F into the displacement, that is L is the original length. So delta L will be the displaced length, like that. Okay. So next, so wherein, so here delta F represents the virtual load applied, and delta is the deflection in the direction of virtual load applied, and delta L is the deformation of the internal element, deformation of the internal element, which is I have going to consider it. Apart from C, I am also consider the internal element, wherein that length is equal to L, and delta L will represent the deformation of that element with reference to the delta F. So delta small f, it represents the virtual elementary forces of this element. Okay. So now if I just take delta F, that is this delta F, which is applied exactly on point C as equal to 1. Suppose if I just take delta F, since it is arbitrary, and if I just take for convenience delta F is equal to unit load, that is equal to 1, so that the equation could be rewritten as 1 into delta is equal to the sigma f into delta L. So wherein this is the right side, wherein F denotes the internal force due to the virtual unit load. Sigma f denotes the internal force in the members due to the virtual unit load, wherein delta F will be equal to 1 if since it is a assumed load. So I just assume it as equal to 1 because it is a unit load method. So therefore, small f represents here as the internal force in the member due to the virtual unit load. And the right hand side of the equation will directly provide the displacement of point C due to the applied external load. So therefore, this method is called as unit load method. So this load is called as unit load method. So left hand side, it represents the displacement of this point C due to the unit load applied. So right hand side of the equation provides the displacement of point C to the total overall load. So this is what the representation. So in order to find the rotation, so in this equation we can find the displacement. So in order to find the rotation, that is slope, so I just take delta in place of delta as theta. Similarly, in order to find out the rotation at any point of the loaded structure, so in place of theta, I just consider it as delta. So, sorry, in place of delta, I just consider it as theta. So, therefore, 1 into theta will be equal to sigma f into delta L. So, therefore, here in this case, sigma f represents the internal force in the member due to the virtual unit moment or unit rotation applied in the direction of theta. So in this case, in the second case, instead of sigma f or delta f, so I am going to apply the moment of magnitude equal to 1, wherein its rotation is equal to theta, like that. So this is what the representation of the unit load method. Is it clear, all of you? Yes,
Yes.
all of you?
Yes, ma'am.
So this is very important for you for solving the numericals. coming on to the application of this method. So application of this theorem, that is unit load method, to the beams and frames. Suppose here I have just considered here a simply supported beam over here. You can just notice a simply supported beam. So this simply supported beam is having the it is having the length of equal to L. It is having the length of equal to L. So this simply supported beam is also considered to be having the uniformly distributed load of magnitude equal to W. So here you can just notice over here, C is the midpoint over here. So I need to consider, or I need to calculate what is the amount of deflection which is caused due to the application of load. So therefore delta CV, C is the point wherein we are supposed to calculate the deflection. V represents the vertical force, the force in the vertical direction. So delta CV is equal to the internal force or the internal deflection which is caused due to the application of force. So here the internal virtual work is considered mainly due to the bending, and it is caused due to the internal moments, that is mu is the internal moment due to the unit load which is applied, and it is undergoing the rotation of d theta. So here if I just take off this overall UDL, and then if I just replace that overall UDL with that of the unit load, then I'll get the value as MP is the moment due to the applied force. So MP is the moment due to this applied force, that is a real force. Okay. So mu represents the moment due to the internal force. Internal force is that it is a force due to the unit load. Okay. So d theta represents the rotation which is caused due to the application of internal force. So d theta represents the rotation or the slope which is caused due to the application of this moment, that is due to the load of 1 kilonewton. Okay, so here we know that d theta from the previous, that is the application of moment area method, we know that slope d theta is equal to m by ei diagram. Okay, so but here we know that dx is the has to be considered. Dx has to be considered since x is the distance wherein we are going to, dx is a small distance. Dx is a small distance on the application of the unit load. So therefore we are going to consider mp into dx divided by ei, m by ei times of dx, wherein dx is the small length of the C wherein the unit load is applied. Okay, so here the displacement of C is called as, the displacement of C is 1 into delta CV, 1 into delta CV into 1 into delta CV is the displacement of C due to the application of unit load, that is 1 in times of delta CV into the 0 to L, that is the integration value of 0 to L times of mu into d theta, moment multiplied by the slope, gives you the deflection due to the unit load applied. So here delta CV, 1 into delta CV is the value due to the unit load, is equal to mu multiplied by d theta value, we know it as mp multiplied by dx into dx divided by ei. So this is the value of the displacement of the C which is caused due to the application of the real force as well as the virtual force of magnitude equal to 1. Is it clear, all of you?
Yes,
Yes.
ma'am.
Shall I proceed?
Yes, ma'am.
So this is a very important step. Here we are supposed to follow some important steps in order to determine the slope and deflection of a unit load. First and foremost important step is that we are supposed to calculate the bending moment, that is MP, due to the real force. Means what is the amount of force which is given in the beam or in the frame. So for that real force, we are supposed to determine what is the amount of moment, that is bending moment. So here next step is that we are supposed to determine the bending moment due to the unit load applied in the direction of the required displacement or slope. Suppose in the question, if they have asked, so in the previous slide itself they have they have determined the displacement exactly at the midpoint. So somewhere if we want to find out exactly like in the midpoint means we are supposed to add the unit load exactly on the point where we are required to find out the displacement and the slope, and then for that unit load we are supposed to calculate what is the amount of slope and deflection. So the next thing is that we are supposed to find out the integral of mu multiplied by d theta. So here in order to find out the value of the deflection and the slope, we are supposed to compute this value, that is mu is the moment due to the unit load, and mp is the moment due to the apply that is a real load. Okay, so that integral part you are supposed to determine. So next thing is that for getting the desired displacement. So next thing is that the bending moment shall be taken as positive if it is sagging, and it is taken as negative if it is hogging. As in case of beams, the bending moment is taken as positive value if it is a sagging moment, and if it is hogging, if it is hogging, it will be taken to be as the negative value. So the last thing is that the positive value of this integral part, if at all, if you get this integral part, it represents the deflection. So if you get the positive value of this calculated value, so it represents that the displacement is in the direction of force applied. Means suppose if you are applying the force in the downward direction, so in that direction itself, if you get the value, means if you apply the force in a downward direction, then the moment will be in the sagging position. So therefore you will get the displacement. So if at all, if you get the displacement in that direction itself, so then it will be taken to be considered to be as positive. So suppose if you are applying the load in the downward direction, but if you are getting the displacement in the other direction, means the hogging direction, so then that type of displacement will be considered to be as negative displacement. Is it clear, all of you? So these are some of the steps. First thing, we are going to determine what is the bending moment for the real load. Second thing, you need to apply the unit load to the point wherein we are going to compute the slope and deflection. So third point is that we are supposed to determine the deflection by using the integral part which we have calculated. So fourth thing, the sign convention for the sagging moment is considered to be as positive, and hogging is considered to be as negative. And fifth one is that positive value of the displacement indicates that the direction, it is in the direction of the applied load. If suppose the displacement, if it is in the opposite direction of the applied load,